All right, we'll go ahead and get started. Good afternoon. I'd like to thank everybody for joining us today. Before we get started, I'd like to introduce you to our speakers today. My name is Philip Richardson. I'm Associate Principal Engineer here in our High Voltage Design Group. I'm based out of Minnesota. Have about 2 years experience here at Revamp and about 23 years of experience in the power industry. Azim?
Hi everyone, my name is Azim Shahab. I'm a Senior Power Systems Engineer at Revamp and have been with Revamp for a little less than a year and have been in the power system industry for about 15 years. And I'm based out of Toronto, Canada. I pass it over to Udit.
Hey everyone, I'm Udit Dangarwala. I'm also a Senior Power Systems Engineer at Revamp. I've been working at Revamp since 4.5 years, and I'm based out of Austin, Texas. I've been working in the renewable energy and power systems industry since a little over 5 years now. I'll hand it back to Philip to go over the agenda for today's webinar.
Thanks, Udit. So today our team's going to walk through you all a high-level view of the power system studies that influence high voltage substation engineering and discuss how those results impact our design. A few housekeeping notes first. Please utilize the QA feature of the Teams meeting to submit question while the presentation is going on. If the QA doesn't work for you, just use the chat. We'll have time at the end to address those questions and for people to come off mute and ask additional questions. We're happy to offer professional development credits for the webinar today. If you're looking to obtain a certificate of completion, or if you just have more questions about Revamp, please reach out to Chloe. Her email is posted in the chat. Before we dive into the content, I want to take a moment to introduce you to Revamp. Revamp is a utility-scale renewable engineering firm founded in 2016. Since then, we have issued detailed designs for over 26 gigawatts of utility-scaled renewable projects. Our development team has completed nearly 300 gigawatts of renewable designs. Our team of nearly 150 professionals are driven by commitments to deliver resilient, high-performance systems that meet today's energy demands and provides for a sustainable future. Our services cover the full spectrum of engineering and technical support needed for utility-scale renewable projects, from the PV and BESS panels to the transmission interconnection, including transmission line design, substation design, relay settings, compliance, power system design, and everything that entails. And with that said, I'll pass it over to Judith to get started with an overview of the power system studies.
Thanks, Philip. As Philip said, we'll be going through an overview of power systems engineering first. Can you please go to the next slide? So power systems, by definition, is a network of electrical components that generate, transmit, and distribute electrical energy. Some of the key components of power systems include generators, both synchronous and asynchronous, transformers, transmission lines, protective devices like breakers and relays, reactive power support devices, and loads. Power system studies or analysis are calculations that we perform on this network to evaluate the system performance and assess the various components for reliability and safety. These calculations allow us to identify any potential issues and mitigate them. Next slide, please. This slide shows the list of typical studies that are performed for a HV and substation project. These studies include short circuit analysis, arc flash analysis, load flow and reactive power study, harmonics analysis, cable ampacity study, grounding analysis, insulation coordination and temporary overvoltage study, lightning protection study, and NERC compliance studies. The typical software that are used for these studies include ETAP, SKM, PSSE, PSLF, and Aspen OneLiner. For transient studies, we have PSCAD. For cable ampacity analysis, we typically use SimCap and AmCalc, CDEX and WinIGS for grounding analysis, and we have Autodesk SDS for lightning protection studies. Next, we'll go through an overview of each of these studies. Next slide, please. First up, we have short circuit analysis. For short circuit analysis, the system is studied under faulted condition, and the analysis is performed to evaluate the thermal and mechanical stresses that the equipment may experience under fault conditions. The goal of the analysis is to evaluate fault levels under different types of faults and compare them to the equipment withstand capability. The analysis also helps us determine the ratings for the protective equipment like breakers and disconnect switches. It also allows us to identify issues such as high fault levels and mitigate them. When performing the analysis, we also calculate the coefficient of grounding to ensure that the system is effectively grounded when needed. We also calculate the short circuit ratio for the project to ensure that the inverters are able to operate as intended. Next slide, please. Some of the inputs that impact the short circuit analysis results include fault contribution from the grid and the inverters, the system impedances, which are made up of transformers, transmission lines, and underground cables, the overall substation configuration, for example, presence of a bus tie switch on the MV side or multiple main power transformers, and the overall fault clearing time and equipment withstand limits at those fault clearing times. The short circuit analysis impacts multiple components inside substation. For example, presence of current limiting devices like current limiting reactors and current limiting fuses to reduce the three-phase fault levels. The need of a neutral grounding reactor to reduce line to ground or line to ground fault levels. The ratings for breakers and disconnect switches. The substation busbar withstand rating and the supporting structure design to withstand the associated mechanical stresses. The main power transformer withstand rating. It also impacts the overall substation feeder arrangement at the substation and the grounding design. Next slide, please. This slide shows the components that are modeled to perform a short circuit analysis. Starting from the top, we have the grid fault contribution modeled as a Thevenin equivalent. Going down, we have the transmission line, followed by the HV side protective equipment, which includes the CTs, PTs, relays, and the breaker. Then we have the main power transformer. And on the medium voltage side, we have the associated medium voltage side protective equipment. Then downstream of that, we have current limiting devices. A current limiting reactor is shown here. And followed by that, we have the feeder protective devices, which include the disconnect switches, breakers, and associated relays. These components are necessary to be modeled to ensure that we are calculating the fault levels accurately. Next slide, please. The next study that we perform for substation design is the arc flash analysis. For arc flash analysis, the system is again studied under fault condition, and the analysis is performed to evaluate personnel safety. The goal of the analysis is to calculate the arc flash hazard incident energy and the hazard category rating. Based on the incident energy values and the voltage at equipment, the personal protective equipment or PPE, which is required for accessing that equipment, is determined. Next slide, please. There are multiple methodologies for performing arc flash analysis. For AC arc flash analysis, for equipment with voltages less than or equal to 15 kV, typically the method prescribed in IEEE standard 1584 is preferred. For voltages greater than 15 kV, ETAP arc fault or arc pro method, which are compliant with the OSHA requirements, are preferred. The typical DC arc flash methodologies include pocket method, Stokes and Openlander method, and the maximum power method. Some of the inputs which impact the results and incident energy values for arc flash are the available fault levels at each equipment, the protective device and their isolation at each of these equipments, the working distance at which the incident energy values are calculated, the equipment dimensions, electrode gaps and electrode configurations, and the fault clearing time. It should be noted that for equipment where the fault clearing time exceeds 2 seconds, a 2-second max can be utilized to calculate the incident energy for NFPA 70E. Arc flash analysis majorly impacts the relay settings at the substation. Given the incident energy is directly proportional to the fault clearing time, reducing the fault clearing time by changing the relay settings can reduce the overall incident energy levels across the system. Also, specific modes can be programmed in relay during maintenance so that the fault clearing time and incident energy levels are really low when equipment needs to be accessed for maintenance. Next slide, please. The next study we have is load flow and reactive power study. For this study, the system is studied under steady-state normal conditions. The analysis is performed to ensure compliance with requirements and standards and to ensure that none of the equipment limits are exceeded. The goal of the study is to evaluate the overall plant performance in terms of losses, efficiency, and the voltage profile across the systems. The study is also performed to ensure that the voltage and current limits of any of the equipments are not exceeded. The reactive power study is performed to ensure that the reactive power requirements are met at the POI. Next slide, please. Some of the key considerations for load flow analysis include the losses. Given that the losses are tied into the financial model of the plant, it is critical to ensure that the losses that are calculated are less than the required losses for this financial modeling. Another consideration is the equipment capability and ratings under different ambient conditions. Given that the equipment may be derated at certain temperature and altitude, this needs to be considered. One of the critical inputs or considerations for reactive power analysis is the inverter reactive power capability at high temperatures. Given the PV modules are not able to produce high voltages at high temperatures, the inverter reactive power capability can be impacted due to that. And that is critical to consider for reactive power analysis. Revamp will be publishing a white paper on this soon. Other considerations for reactive power analysis include the reactive power requirements for non-synchronous and inverter-based resources, which are identified in FERC Order Number 827 and IEEE Standard 2800. Also, any project-specific reactive power requirements should also be considered, which can be found in the interconnection agreement for the project. Reactive power analysis determines whether a capacitor bank is needed at the substation, and if required, what will be the size of it. It also informs the main power transformer's tap changer settings, be it for the load tap changer or the position of the de-energized tap changer. Also, if any loads or aux loads need to be fed within the plant, the aux equipment can be sized using the load flow study. Next slide, please. The next study that we have for designing the substations is harmonics analysis. For this study also, the system is studied under steady state normal condition, and the study is performed to ensure compliance with the required standards. It is also studied to identify any overheating due to harmonic losses. The goal of the study is to calculate the voltage and current harmonics in the system and compare them against permissible thresholds provided in IEEE Standard 519 and IEEE Standard 2800 for inverter-based resources. Once the analysis is performed, if any of the harmonic orders or overall harmonics are exceeding this threshold, then mitigation can be suggested in terms of filter circuits. Next slide, please. Some of the inputs that can impact the harmonics in the plant are the grid harmonic profile, the inverter-based resource harmonic profile, and the presence or absence of a capacitor bank at the substation. Due to the presence of a capacitor bank, the impedance profile of the system can look very different under different harmonic orders. As a result, there might be resonant conditions for some harmonic orders, and that may result in harmonics exceeding the permissible thresholds. Also, harmonic analysis can be performed pre-construction or post-construction. For pre-construction harmonics, a harmonic load flow is simulated in a software, and the total harmonic distortion and total demand distortion are calculated using aggregation formulas provided by IEC. For the post-construction harmonics, once the generation begins, a testing plan is developed and the harmonic data is measured in the field. That data is then post-processed and compared to the requirements in the various standards to ensure that the plant is able to meet, and if the harmonics are exceeding, then mitigation is suggested. Harmonic analysis determines whether a filter circuit is required at the substation, and if so, whether it is required to suppress the overall harmonics or to target particular harmonics. For US mainland projects, which are utility-scale solar and battery energy storage projects, typically a tertiary delta winding is provided in the main power transformer at the substation to capture the triplen harmonics. Also, harmonic analysis can determine whether there would be any potential overheating in the substation equipment due to harmonic losses. I'll now pass it on to Azim to go over the remaining studies.
Thanks, Udit. The next study that we are going to discuss for the purpose of HV substation design is cable ampacity study. This study is performed under steady state conditions to evaluate the thermal loading on the cables and ensure that the temperature ratings are not exceeded. The goal of this study is to determine proper loading and spacing of the cables in order to prevent any damages that might occur to the cables due to overheating. Some of the key factors that we typically consider in this study include the soil thermal resistivity, which we typically get the values for from the geotech reports, load factor, insulation thermal ratings, the conductor in the cable, and the physical arrangement of the cable installation and the parallel runs. Once we perform this study, the impact that the result might have on the design of the substation include cable spacing. We might decide to modify the cable spacing due to the results of this study. Also, selection of backfill material with lower thermal resistivity compared to native soil, as well as changing the cable size. Next slide, please. The next study that we are going to discuss is grounding study. This study is performed for the system under fault condition and to ensure safety. Basically, the goal of this study is to ensure that the grounding system of the substation is designed sufficiently to ensure safety of people in terms of the step and touch voltages that they get exposed to during a short circuit fault event. And we do this study in compliance with IEEE 80. Next slide, please. The key factors that we typically consider in this study include the duration of fault or the fault clearing time, the fault current levels, the soil modeling based on the electrical resistivities of soil, which we would typically get from geotech reports. Also, transfer of potential and induced voltages due to nearby transmission lines or even underground cables. On the right side of the slide, you see plots generated by the grounding studies software CDEX showing the step and touch voltages during a fault event at the substation. Once we perform this study, the impact that the results might have on the design of the substation include potentially modifying the design of the ground grid mesh, or adding more grounding rods or surface materials such as gravel, or even changing the ground conductor size. Next slide, please. The next study that we're going to discuss is insulation coordination and temporary overvoltage. These studies are performed considering system is under abnormal or fault condition to ensure that the equipment are well protected. The goal of this study is to confirm the selection of the minimum insulation strengths of equipment and that the surge arrestor ratings are adequately selected to withstand the expected temporary overvoltages as outlined in IEEE C62.22. Also, to evaluate the ability of surge arrestors to withstand temporary overvoltages and discharges of energy that might happen during a load rejection condition or short circuit fault. The key factors that we typically consider when we perform this study are the voltage ratings of the equipment, as well as the overvoltage withstand levels and the ratings of the surge arrestors. Once we perform this study, the impact that it has on the substation design includes the surge arrestor selection and their ratings. Next slide, please. The next study that we are going to discuss is lightning protection. In this study, we analyzed the system under transient condition to ensure safety and equipment protection. Basically, the goal of this study is to confirm that the substation shielding arrangement, which typically includes lightning masts and shielding wires, is sufficient for protection from direct lightning strikes. And we do this study in compliance with IEEE 998 and NFPA 780. The key factors that we would typically consider in this study include the BIL levels or basic installation levels of substation equipment, as well as the physical arrangement of substation equipment, including their elevations and the height of lighting masts and shielding wire. Once we perform this study, the impact on the substation design can include modifying the arrangement of lightning masts or shielding wires or adjusting their heights. Next slide, please. We perform additional studies and the first two studies listed here, TRV and lighting over voltage using PSGAD. We do them if required by the client or if there is a project-specific requirement. We also perform NER compliance studies, which are typically performed at commissioning or post-commissioning and include facility rating studies, mod studies, and PRC studies. I'm going to pass it over to Philip to discuss the impact of the studies on the HV substation design in further details.
Thanks, Azine. So how did the studies impact the substation design? On the design side, what are we doing with the study results? Basically, we're verifying our design from equipment selection and their specifications such as ampacity and short circuit ratings to the lightning protection design, ground grid design, relay settings such as pickup and clearing times, voltage regulating settings of the transformer, LTC, and capacitor bank relay settings for automatic reactive power support. So the ampacity study is used to verify substation rigid and strain buses, jumper ratings, and also determines our underground feeder exit design. Prior to the study, we'll choose ampacity ratings based on maximum continuous current that will flow through the equipment. This will vary based on the location of the equipment and the methodology used. For example, for a 2-transformer substation, the line disconnect switch will see more current than either of the high side transformer disconnect switches. Short circuit ratings or short circuit study is needed to determine the equipment's short circuit rating, its max fault clearing capabilities, whether that's 25, 40, 50, 63 kA. Bus location supports also needed to determine ground grid design, whether a grounding transformer is needed and its specifications. Helps determine our fuse selection. Helps us determine what our relay settings will be, how quickly a fault needs to be cleared to protect equipment from damage. The short circuit study is also used to identify potential CT saturation. Udit and Azine covered these studies. So the installation coordination study, again, helps determine the equipment BIL rating. There is a standard rating range for different voltages, as you can see on the right. TOV studies used to determine surge arrestor MCOB ratings. And the power flow studies used to determine if a cabinet is required and its size. And it's also used to determine the transformer low tap changer settings. Again, the grounding study will help determine the ground grid design, how much copper needs to go in the ground, the rock resistivity, how much rock you need, whether you need 2 inches of rock or 4 inches of rock. That study will help determine that. For equipment maximum voltage rating, there's no study. You know what nominal voltages you're connecting at, whether that's 115 kV, 230, 345 kV, etc. Substation equipment has a standard maximum rated voltage associated with a nominal voltage. There are times where you may exceed the standard maximum voltage rating and may have to specify higher voltage requirements. For example, one of our recent 345 kV projects, the interconnecting utility had a voltage schedule that ran up to almost 6% over nominal. And as you can see at 345, the max rating for standard equipment is about 4.7%. So for that particular project, we had to specify a higher maximum voltage range for the 345 kV equipment. So what design considerations do we take into account because of the results of the studies? So 10 to 30% design. Usually the substation design at this stage are done with minimum input from the studies group. So the sub-design team has to rely on best practices and engineering judgment for the design and equipment ratings and specifications. For short circuit ratings, we'll use the system impact study, facility study, or utility provided short circuit contribution, and then we apply a growth factor to that, usually about 20%, unless the client decides to provide one for us. If the information is not provided, we'll either use 40 kA for equipment rating, or if lead time is an issue, we'll use 63 kA. For the medium voltage equipment, we also consider the main power transformer's impedance and the PV or BESS plant rating. Again, if the information is not provided, we'll assume 40 kA for the ratings. If a client has rating standards they want to use, or if they already procured equipment, we'll use those ratings as part of our design. Capacity rating. So we touched on this previous slide, but I want to emphasize what methodology we use. So for the high side, we have 2 choices. We can either use the main power transformer top MVA rating or the point of interconnection rating. One thing we need to know is if there's any future plans to increase the POI rating over future phases. For example, if phase 1 is a 200 MVA project, and there's a potential for phase 2 of another 200 MVA, should we design the affected equipment to 400 MVA? For the transformer low side and medium voltage bus, we'll size the capacity rating based on the top MVA rating of the transformer at that voltage. For feeder circuit breakers and switches, we'll size it according to the generation on the feeder. And then for feeders themselves, we'll assume 20 to 25 MVA per feeder, but this is something the client may specify. Again, equipment will see different current based on its location. During the 10 to 30% design stages for BIL MCOV ratings, we'll use standard values and to be determined for the NGR. We need the study results to actually, to provide proper specifications for these equipment. For CTs, the CTs are sized between a balance of the expected continuous current and the expected fault current. And I'll explain this a little bit later in a different slide. The capacity rating of the CT is determined by the CTR, the primary CTR, and the thermal rating factor. For example, the 800 to 5 CT with a thermal rating factor of 2, it can handle up to 1600 amps of continuous current. The CT's accuracy, class, and burden determine how much secondary voltage the CT can handle at the maximum rated voltage. Basically, how well it can convert primary current into secondary current. The higher its rating, the better it is. This is especially true for CT saturation for high fault current and burden. Unless the client specifies the ratings, for high voltage equipment, we'll assume a C800 CT, and for medium voltage, C400 CT for protection CTs. And if it's a metering CT, we'll specify 0.3 accuracy with a burden of 1.8. So buses are sized to carry the expected maximum continuous current that will flow through it, and with some fudge. At this stage, bus support location is based on the bus size. For example, for a 6-inch bus, we don't do spans greater than 45 feet between bus supports. For underground feeder exit designs, we design that with quote unquote standard spacing. Our standard is to space them as far apart as we can. Typically, we shoot for about 8 feet of spacing, which most of the time on our designs is sufficient. Again, we need the ampacity study and short circuit studies to confirm this part of our design. So potential issues after 30%. So after 30% design, we start receiving some of the power system studies. What are some of the issues that we may address? Even though we identify these as potential issues, these are just a normal part of our substation design process. One thing we have to consider is the current transformer ratings, the CTR. So due to the short circuit contribution and how much current flows through the CT for a particular fault, CT CTR, accuracy class, and burden, a CT may saturate during the fault. So basically what that is, it's the actual primary current of the fault. The relay is not able to measure that correctly on the secondary side. So what this can do is cause the relay to be slow to operate, which based on the total clearing time required to protect equipment, that slow to operation may cause equipment to be damaged. Also, if a CT saturates that's connected to a transformer differential or bus differential, it may misoperate. It may trip for faults outside of its zone of protection, thus tripping off more devices than is needed to clear the fault. Another issue is if the CT connected to a particular relay, if the CTR is too high. So if the CTR is high, the remote in fault is low, the relay's secondary set point might not be sufficient to provide protection. So for example, if the remote in fault is 500 amps and you have a CTR of 400, you may not be able to set the relay for adequate fault coverage. Cat bank. So to determine the size of the cat bank, a reactive power flow study is required. This study is highly dependent on the PV or BESS design and inverter selections. One issue is the timing of the substation project versus the PV or BESS. So if the PV or BESS design is lagging the substation project too much, to identify whether that cat bank's needed or not, it may become a procurement issue if a cat bank indeed is needed. Fuse cutouts. So fuses have a specific interrupt rating, that vary from manufacturer to manufacturer, but usually the highest fuse cutouts you can get is about 33.5 Ka. So we have to be very selective in the fuses we specify. For short circuit ratings that exceed this, you may have to install a current limiting fuse in line with the main fuse so that ratings aren't exceeded. Bus design. So the short circuit study helps determine bus support locations to prevent mechanical stresses during fault. And the short circuit study determines that we need closer spans. Well, more steel and foundation may be needed. Underground feeder exits. So if the ampacity study comes back with lower ratings based on the design, then we may have to alter our feeder exit, having a wider space between the phases, etc. PV and BESS equipment rating. So what we do in the substation affects the PV and BESS ratings. Luckily on the substation side, we can get equipment rated up to 40, 63 Ka. But on the PV and BESS side, typical top is about 25 Ka. So if the short circuit contribution or faults on the PV or BESS side is greater than 25 Ka, then we may need to apply short circuit mitigation at the substation. Ground grid. So both the ground grid design and grounding study is performed in parallel after the 30%. So kind of the design feeds into the study and vice versa until the design is correct. But as part of the study, the resistivity of the rock will be specified. Once this is procured, the actual rock resistance values will be tested, and that will be fed back into the study to verify the design. One thing I want to mention here about rock, it doesn't seem that important, but it's a very detailed part of your design. Last year I was on site for site support, and I was just walking the yard. I kind of noticed that the rock just seemed just very tiny, and also due to all the rain, the yard had a lot of mud in it. Well, it turns out the wrong rock was installed, so construction had to take all that rock up from the yard that's already been installed and install new rock. So, if you're ever out of a site visit, kind of pay attention to that, because that rock design is very crucial to the ground grid study. Study results. Again, review the study results. We'll verify our design, equipment ratings. We'll, the study results will identify issues brought up and what needs to be done to address them. As stated earlier, some of the items brought up during the studies is just a normal process of our design, but there may be issues brought up where mitigating the issue may vary. Short circuit contribution plays a big part of the substation design, especially reducing the fault currents for the PV and BESS system. So this is one of the most common issues that's brought up that needs to be mitigated. As Udit mentioned earlier, the NGR is used to reduce zero sequence fault current. This is very important to prevent the underground cable concentric neutral. The NGR is typically always included in the design of the PV and BESS projects. Current limiting reactors, that isn't typically a part of the design, but it may be required to lower the fault current. Considerations of where to place the CLR may vary, so you can place it either on the low side of the transformer to reduce the fault current in all medium voltage equipment, or maybe one of your PV or BESS feeders is just a particular short run where only the equipment on that feeder is exceeded. So in that situation, you may just install the CLR just on that particular feeder instead of just on the low side of the bus. The CLF, kind of already discussed that. Again, it's there to limit fault current for a fuse to remain in its ratings. Short circuit transformer impedance. So increasing the transformer impedance is another way to mitigate high fault current. Higher impedance equals lower short circuit. The pros of applying this method is that, obviously you're going to lower your short circuit. Other pros is the likelihood of needing a CLR goes down. If you size the impedance right on the transformer, then it should take care of the short circuit issues downstream. Higher impedance, you need a smaller NGR, again, reducing zero circuit fault current contribution. If you know what the impedance is, it helps to be better informed with the LTC selections. Cons, well, it's going to cost more. You have more impedance. You're going to have more loss, higher voltage drop. More likely the transformer may need to be larger. You increase the likelihood of needing a cap bank. And I guess one of the most important things is this has got to be decided early on due to lead times. So, usually before the engineer of record, the design firm has been brought on, that decision has to be made. Another way, to reduce short circuit contribution is cable impedance. You're adding more cable length to your feeders. This option may be less expensive and easier to implement versus other methods. And one thing to note, that this doesn't increase or decrease the likelihood of needing it might decrease the likelihood of needing a cap bank based on how much the capacitance of the cable that you're adding, but it's not going to be increasing the need of a cap bank. One con is you need to have the space to run more cable underground. Arc flash, as mentioned earlier, as your fault current and clearing time increases, the incident energy level associated with the fault goes up. One easy way to mitigate arc flash is reduce the short circuit. Another method, which Udit touched on, was your protection settings to enable a maintenance mode. Maybe when you're going to be working on a particular circuit, you enable the maintenance mode, which allows the relay to pick up on a lower pickup value and trip faster. One thing I want to note here is the best way to prevent arc flash is to don't allow maintenance while the circuit's hot. Nameplate and capacity ratings. So most equipment and capacity ratings is per specific parameters, based on the material used, the site parameters. So based on the site conditions and the equipment, you may be able to exceed the nameplate rating. For example, switches after 1975, the material in the switch design changed. So the actual capacity rating of the switch is about 8% over nameplate at 40 degrees C. So based on your site conditions, you may be able to exceed that nameplate. One thing to note is, as part of your FAC 8 requirements, your compliance requirements, you have to document your rating philosophy and the actual QB ratings. So if you're going to change, take a step back. The easiest thing for your FAC 8 ratings is just use nameplate. So if you decided to not use nameplate, to use some other methodology, you have to document that. And one thing to note that this is site specific. CTR protection issues. We kind of brought this up previously, but I want to mention it again. So if there's CT saturation issues, how do you mitigate it? The easiest thing to do is just use better CTs. Use a C800 CT instead of C400. Make sure you're properly choosing your CTR. Another way is most of your modern day differential relays, whether it's bus differential or transformer differentials, have CT saturation logic. So enable that. Another thing you can do is delay tripping, which is basically kind of what the CT saturation logic does. What else is there? Fault detection. I brought that up. Size your CTR based on your remote fault, and so you can actually see the fault. But one thing to mention, if you use a lower CT, you have to be concerned about CT saturation. So with that, this concludes our presentation on power system engineering and studies for high voltage design. Let's see what questions we have. Udit?
Hey, yep. I've been monitoring the chat. Excuse me. So yeah, we do have a few questions on the studies. We can start with the first one on harmonics. The question is, in harmonic studies, how do you handle the Norton equivalent impedance of the inverter and things like frequency dependency of cable impedances and capacitance of transformer windings? That's a really good question. So some softwares like ETAP do not allow that level of modeling. However, more sophisticated softwares like PSCAD can be utilized. So for greater accuracy, these elements can actually be modeled in PSCAD as capacitances and inductors rather than just reactor or reactances. And that way the frequency dependency can be accounted for. In any case, the pre-construction version or the desktop version that we perform is just a very high-level indicative study because the harmonics in the field get added vectorially. So there's still a lot of estimation that goes on this study. However, if a filter circuit design needs to be prepared before construction, then we do recommend using softwares like PSCAD that allow us to account for these things and then model them more accurately and give a better representation. However, we always recommend that to get an actual sense of harmonics within the system, it is always good to perform a post-generation study where we actually get the data measured in the field and then process it to calculate the overall harmonics. I hope that answers the question. Yeah, please feel free to follow up in the chat if there's any follow-ups. Other question we have is at the substation. So if a substation requires grading fill and compaction, do you need to know the properties of the proposed material and conditions prior to design? Or can you make adjustments to the in situ geotechnical results? Azim, can you please take that on?
Yeah, for sure. That's a good question. Ideally, if the substation requires grading, fill, and compaction, it's much better that if we know about it earlier in the design, because the earlier we know, the more optimized design we can provide. However, if we don't get that prior to the design, there might be some adjustments that we can make because obviously the thermal properties of the grading field would be different than what we have considered based on the geotech report. So we might need to make adjustments to the design. We might need to call for example, backfill material at the cable location or adjust the cable spacing, something like that. It's really dependent on the project conditions, on the design. It's a case-by-case basis, but it's much better if we know it early on. I hope I answered the question.
Thanks, Azin. Then we have a question on DC arc flash. For the DC arc flash study, if the arcing current is very low at DC combiner box, can we go with a 2-second fault clearing time to find out the incident energy at the DC combiner? So that's a really good question, especially for PV designs. The fuses typically will not clear an arcing fault at the combiner box. And as a result, fault clearing time would not be able to be determined in a software. So that's why the provision in NFPA 70E comes in handy. So the 2-second guidance that is provided is based on like the time to react when an arcing fault is seen. So 2 seconds is enough for a person to react and move away from the arcing region. So yes, we can definitely use the 2-second rule to determine the incident energy at combiner boxes. Okay, I see one more question in the chat regarding a reactive power. So for reactive power study, once the model is built and a case is ran, how can we check the impact of varying power factors for the total reactive power needs? So assuming that the question where it says varying power factors, it is meant to be at the inverter output terminals. So within the software, there is a facility to dispatch inverters at different set points of real and reactive power. And those can be loaded and multiple cases of load flow can be run. And once the load flow resolves, it gives us the output real power and reactive power at the POI. And that's how varying power factors, at the inverter level, how they impact the actual POI results can be checked in any simulation software. Please feel free to follow up on that. Yeah, if I got the assumption wrong. Okay, I see there's one more question. It says it's not technical, but yeah, we can definitely take that on. So yeah, I think Philip, this one might be for you. If someone is interested in getting into power systems industry without much HV or solar BESS experience, what would you recommend them to follow?
That's you know, I got lucky. I was more of a going to school for computer programming. I just happened to luck up, attended a meeting, and stayed with it. You have the PSE. You have conferences throughout the country. You have if you're interested in a certain company, go to their job board. Reach out directly, and a lot of companies have internships. I'm not sure where you are in your career, whether you're still a young engineer or if you're 20 years ready to switch career paths. I hate to say just be ambitious, but knock on the doors, reach conferences, PSC, associated with colleagues, just asking the question. There are many power system conferences throughout the U.S., many renewable conferences. Attend those, meet and greet. I don't know, Zine or Edith, anything to follow up on?
No, I think you captured it well in terms of just need to start somewhere and then eventually gaining more knowledge and experience within the industry.
I mean, one, I guess, kind of bad things financially, where you are in your career. If you're 20 years switching careers, that may be more challenging than if you're still 1 or 2 years. But if you're thinking about it, do it early.
One thing I wanted to mention is I'm not sure where in your career path you are, but if you're a younger engineer, maybe try getting some experience in a firm that does a variety of projects, including HV or solar work. That way you get exposure to a variety of subjects, including HV and solar, and then from there, maybe you can build it up.
Thank you both. I see new questions are coming in.
So Daniel
Um,
asked, he's interested in what software our team uses to create the 3D models that we're seeing in the slides. So on the physical ones, we use Autodesk Inventor. It's a very cool tool that our physical engineers use. I'm more on the PNC side and protection side, but the 3D stuff he Is there any other questions,
okay.
Udit?
Yep. Yeah, still catching on to the chat. So I see one question regarding ampacity analysis. Is the ampacity you guys perform are only for AC cables, or that also covers DC cables as well? Also, what software you use for power ampacity calculations? Thank you. Azim, would you like to take it on?
Yeah, sure. The software that we use is SimCap, and we also perform the ampacity analysis for both MV and DC cables in the solar projects.
Yep. And yeah, I think our slides only showed medium voltage AC cables for now because this was more geared towards substation. But yes, we do perform analysis for DC cables.
Mm-hmm. Right.
I see a question regarding arc flash regarding the IEEE standard. Why IEEE 1584/2018 is used and not 2022 standard is used. So essentially, the methodology is still provided in the 2018 version. 2022 is more of a guidance document on how to implement that methodology. So the basis of the standard and the calculations and the considerations are still provided within the 2018 standard. That's why that was referenced in this presentation. Yeah, still looking through the chats. Okay, I got a new one. Does ETAP consider inverter contribution during incident energy calculations? As a contribution from the inverter will be cleared within 0.16 seconds for 50% under voltage. How does anti-island of inverter affect incident energy during faults? So yeah, we've had extensive conversations with ETAP regarding inverter contribution for arc flash analysis. So based on our last discussion, it only considers the inverter contribution up to the time when the primary fault clearing device clears the fault. So yeah, it does consider it. However, if the fault clearing time is faster than the 0.16 second mentioned, then it does cut off the contribution at the fault clearing time of the primary fault clearing device. In the second part, how does anti-island of inverter affect incident energy during faults? So that would be a project-specific question. But in terms of when we say anti-islanding, so the low voltage write-through settings specific to that project would need to be considered, as in for how much longer will it write through. So depending on the actual project specifics and the settings that are implemented, that will determine how much energy or how much time the inverter will still contribute to the arc fault. I hope that answers the question.
We'll give it, there's another question.
Philip, do you see it?
Yeah, so not a technical one, rather a career-related one. Should a study engineer need to know how to perform all the studies mentioned, or there are different groups to focus on different studies? Where should an entry-level engineer study to get started? I can, so I started my career out just performing short circuit studies using CAPE. It was more the on-the-job training. And then my second job, I started to learn how to use Aspen. And this job, I learned how to use ETAP. But, you know, Udit, I'll let you cover how we do it here at Revamp.
So at Revamp, yes. Everyone more or less does get exposure to different types of studies. Definitely everyone starts with one study. And then as the project progresses, so yeah, the way it is, like the studies engineer are associated with the project entirely. So as and when the time comes or the design develops, they do get exposed to different types of studies. But yeah, for me also, believe I started with performing load flows, just load flows, and then I definitely got into all the different studies like short circuit, arc flash, ampacity analysis, grounding, all of those. Azine, would you like to add anything?
Yeah, just like Odit said, there are certain studies that most of the studies people in our team perform, such as thermal studies, short circuit, load flow. And then there are some other studies that are a little more specialized, such as TOB or grounding. So to answer your question on where should an entry-level study engineer get started, I would say on the more general studies, such as load flow, thermal, short circuit.
Thanks, Azine. I think, yeah, those were all the questions.
Well, I think we're running out of time, so we'd like to thank everybody who attended. Hope you learned something. Again, if you have any other questions about Revamp or this particular topic particularly, please reach out to Chloe, and thank you for your time.
Thank you, everyone.
Thank you, everyone.